Okay, so today we are going to continue our lecture. We are going to talk about return to libc attacks. Let me switch this. In the last lecture, we mentioned the buffer overflow attacks. So this is a different method. So return to libc. So here are the topics we are going to cover in this lecture. So in project 1, we have mentioned there is a method to prevent buffer and exploit like the buffer overflow by using something called a non-executable stack or the data execution prevention. So we can, here is a test program. So to run the shell code in the C program, this part is our shell code. We can copy the shell code to the buffer. So the buffer is on the stack. So the code is on the data section, right? So we copy the shell code from data section to the stack. Then we can force the conversion of buffer to a function pointer. We can then call this function pointer. Right. With the executable stack, if we build the program with GCC -d executable stack and the shell code, this will give us a new shell. However, if we compile the program with no executable stack, so when we try to do this again, it's going to cause an exception or segmentation fault. Let's take a quick look. So here we have log into the virtual machine. Say ls. Let's take a quick look at the core shell code source code. So you see here, this is the shell code, right? Here we try to call the shell code. If we do gcc -z exec stack, then call shellcode.c, let's do -o, call shellcode. Okay, let's try to execute this program. So we can get a shell, right? However, if we try to say non-executable stack, let's try to call the shellcode again, we get a segmentation fault. So the non-executable stack is a part of defense called the DEP, or data execution prevention. It's also called a WXOX. So this is the XOR operation. So the DEP basically says two things. First, data cannot be executed. Second, code cannot be written. So those are the two ways. Those are the two ways to introduce new code. Into the process address space. So the DEP can prevent the introduction of new code or the shell code into the victim process. So sometimes this is also called a WXOX. So the memory cannot be both writable and executable. So we know the truth table of WXOX or XOR. So if we get If W is 0, X is 0, we get 0. If W is 0, X is 1, we get a 1, right? So if W is 1, X is 0, we get a 1. If W is 1, X is 1, we get a 0. So if we interpret 1 as allowed, 0 as not allowed, so WXOX means that we allow a piece of memory to be either executable or writable, but not both at the same time. So this is why data execution prevention is also called WXOX. So the DEP usually is implemented in the page table here. So the page table contains a number of attributes like P, present, US is the user or supervisor code, RW, whether the code is writable and readable, XD is execution disabled. Okay, so the other 2 bits are the accessed and the dirty bits. There are a few other bits also. So DEP has a number of limitations. For example, some app needs a executable heap like JIT. So the JIT is actually used very popularly in the modern computer software. So it's in Java, right? Okay, so if it's in Java, it's also in the Android. And also, there is another thing called JavaScript. So modern JavaScript are actually, in most cases, are compiled into a native code. Sometimes it's converted into a WebAssembly, then converted into the native code. So because every browser runs JavaScript engine, so you must have some apps which needs an executable heap. So you need to have a piece of memory on the heap to be writable and executable. It's also not compatible with all the programs. So you can have mixed code and data section. This is especially true for the ARM architecture. So you basically have some memory pages which contains both code and data. So now you have to set this piece of memory to be writable and executable. Okay, so the code data section may also not be page aligned. So this is a problem because permissions or the page attributes, page table attributes are all set on pages. So if it's not aligned, some page will contain code and the rest part of the page will contain data. So this page needs to be writable and executable. So it also doesn't defend against the code reuse attack because DEP prevents injecting new code into the process address space. So it will not defend against the code reuse attack, such as return-to-libc attack and return-oriented programming attacks. This will reuse existing code. So in the return-to-libc, usually they reuse the functions. In the return-oriented programming, they reuse a smaller piece of code gadgets. So it's called gadgets. It's just a piece of a short sequence of code. So to defeat the DEP, we can jump to existing code, such as libc code. In the libc, there are a lot of functions. For example, it has a system function, right? So the system function will execute this command as a new process. So let's take a quick look at the system. Let's take a quick look at the system function. It's main system. Okay, you should be very careful in your program, in your own program, to use the system, right? So because the command is actually executed using the shell, right? So it's being executed using the shell. So if you give a command to system, so the system command will be passed to the shell, so the shell can interpret anything in this command according to its definition. For example, it can have it's basically you can pass in a shell script. So normally it's not what you want to do, right? So instead, in your own program, using execve or other variations of this this API, right? So we have mentioned this in the project 1. Okay, so let's go back to the lecture, to the slides. Okay, so Ret-to-libc is an attack method. It's an attack method, not a vulnerability. So the buffer overflows, integer overflow, or format string vulnerability, they are all vulnerabilities. So the Ret-to-libc is different. It's a way to exploit those vulnerabilities. It's not a vulnerability itself. So you must have an existing vulnerability in order to use the Ret-to-libc attack. So the Ret-to-libc attack basically means that you are going to reuse the existing function, right, to attack some vulnerability. So here we show a buffer overflow, right? So it's overflow the buffer and overwrite the return address instead of jumping into the shellcode, right? So the shellcode. So we know this is not possible with the data execution prevention. Okay, so instead of jumping into the shellcode, now it jumps into the system function in the libc. Okay, so it's actually equivalent, right? So the system function can do anything the shellcode can do. Okay, so here is the vulnerable program. We have a main function which has a buffer of 240 bytes. Then we open the malicious input. We read this input into the buffer. Then we call the vulnerable function. So the vulnerable function has a buffer of 50 bytes and do a string copy of the buffer from the string buffer. Now it can overflow the return address, right? So this is very much similar to the project 1. So if the non-executable stack is switched on and the stack guard is switched off, address randomization is turned off, right? So we can do it in this way: the GCC, no stack protectors, -d non-executable stack, -o stack, and the stack.c. Right? Then we set the randomization to be 0. Okay. Okay, so let's take a quick look. Okay, let's set the randomization to be 0. Okay, here we have the vulnerable program called stack.c. So this is the vulnerable program we have all been very familiar with. Okay, so if we say here we have the exploit code as in the buffer overflow, right? So we have the shell code on the stack. Okay, so let's say gcc-f no stack protector -z exec stack -o stack.c, right? Okay, let's say let's run the exploiter to generate the malicious input. So let's do stack. Okay, we can get a shell, right, as expected. So if we enable non-executable stack, okay, no execute stack, and we try to execute this again, this will lead to a segmentation fault, because in the previous lecture, right? So we put the shellcode on the stack, then we overflow the return address and points it to the shellcode. Because the shellcode is on the stack, now the stack is not executable, so it will cause a segmentation fault. Okay, so let's go back to the slides. Okay, so overview of the attack. So there's a task 1. We need to find the address of the system. Then we can overwrite the return address with the system's address. Right, task B, we need to find the address of the bin sh string. This will be the pyramid to a system function. Right now, we can run the bin sh from the system. So in the task C, we need to construct the argument for system. We need to find the location on the stack to place the bin SSH. Okay, the first task is pretty simple, right? So we can use GDB to print the address of system. Okay, so we also can print the address of exit. Of course, when we use GDB, there is a big assumption. So the assumption here is that GDB will not change the memory layout, specifically where the libc is loaded. Okay, so it's so in this scenario, this assumption actually holds. Okay, but in the other scenario, this might change. As we have mentioned in the project 1 or the buffer overflow, so the GDB will push something on the top of the stack. So this will actually push down the things on the stack, like the return address, the buffer, or the EBP. Okay. So a better way to do this, in my point of view, we can generate a call dump. We can generate a call dump. Then we can use GDB to debug the call dump. Okay, so let's take a quick look. Okay, so here we have a segmentation fault, right? But we didn't generate the call dump yet. Let's say ulimit c unlimited. So this will allow us to generate the call dump, the stack. Now we have our call file. So we can do gdb stack call. Okay, so let's say b, let's say p system. Right, so this will give us the address of libc system. Let's do p exit. So this will give us the address of exit. Okay, so we can try again with gdb and the stack. Let's say set a breakpoint at the main function. Then we can run the program and the p system. Okay, here we actually have the same address. Right, so we actually have the same address. So it means that the GDB will not affect where the libc is loaded. Okay, the second task. The second task is to find the address of bin SSH. We can still use the previous method, right? So we can put bin SSH somewhere on the stack. Okay, but the problem is that in the previous shellcode, right? If you still remember, we actually push the string to the stack. Okay, so we cannot use this method here because we are not allowed to execute any code or any shellcode that introduces the code. But instead, we can put the bin SSH in the environment variable. Okay, we can create an environment variable called myShell. Then we can do export myShell equal to /bin sh. Then we can execute the stack program. When we are doing so, we actually put the environment variable at the top of the stack. Then in the stack function, in the stack program, we can access the environment variable. So the environment variable is actually at a fixed location. Okay, so here we show a program to test this. So we have a main function. We get a shell. So the get env, it's a libc function to get the address of our environment variable. So if the shell is not nil, we can print its value and its address. To run this program, we can build this and output the name to be env55. Okay, and we export myShell equal to bin SSH. Then we can run this .env, this program. It will print out the value and the address. Okay, so we can use this address actually. Okay, so let's take a quick look. Okay, so we have the env ADR program here. So it's exactly the same as what we have in the slides. Okay. Then we can do export my shell equals to bin sh. So if we run env, so the env will print out all the environment variable. We can run env and the grid my shell. You see the my shell has been set to bin SSH, right? If we run the env 55, okay, so we get the value and the address. However, okay, so if we change the name, say mv em55 to env 7777, okay, so we actually will get a different number. So look at this, right? So the address, if the program name is 55, is this address. If the program name is 7777, we get a different address. So why this is the case? So here is what happens. So the environment variable is actually at the very top of the stack. So the environment variable, there are actually a number of strings. Like for example, we have this string called my shell equals to /bin sh. Then the next string, next environment variable is right next to this environment variable. Then we have a second one, a third one, a fourth one, then a fifth one, so on and so forth. So they are packed at the top of the stack. In the in libc, there is a variable called env. It's actually a set of string pointers. It's a set of string pointers. So the first one points to the first environment variable on the top of the stack. The second one points to the second environment variable. The third points to the third one, so on and so forth. So the last element in the environment variable will be a 0. Say no more environment variable. Right, so now the get environment function, it's basically a string search. It searches through those functions and do a quick match or the pattern match to find the environment variable we are looking for. Okay? So this is why if we are running GDB, right? If we are running a program under GDB, it will actually push a little bit more environment variables to the top of the stack. When you're doing this, it's going to add more content to the top of the stack. This will push down the stack a little bit. Okay, so let's take a quick look at the. Again, keep in mind this layout. Right, let's do a GDB. Okay, let's say set a breakpoint as the main function. Let's do let's execute it. Then let's say p env. Okay, so you see the environment variable. So it's actually a global variable in the libc. And so we didn't define this variable. It's defined in the libc function. So this is the address of the environment variable. So as we have mentioned, right? So this will be the array here. So this is at zxbff3dc. Okay. So if we x say 32a, so here we see the first environment variable is located here. Okay, so the address of bff3d. So we can actually print this x. So the x is the command of GDB to display the memory. So by using this command, we basically print out the 32 integers at the address of environment as addresses. Okay, so this will be the address of the first environment variable. Then we can do xs envion 0. Okay, so this will be the first environment variable. If we look at the here, look at the output here. So this will be the first environment variable, right? Then we can print the second one. Okay, so the second one will be the Android home. Okay, so we can also do a xs. We can copy the address here. If we do this, this will also print the same environment variable as environment 0, right? Okay, so we can also calculate the length of this environment variable string. So let's say this is 2, 4, 6, 8, 10, 12, 14, 16. So the length of this environment variable is 17 bytes, including the ending 0, right? So if we do p plus 17, we get this address. So look here, the second entry in the environment pointer will be exactly this address. So this means that this proof. So the environment variable is actually packed at the top of the stack. Okay, so let's go back to the lecture here. Okay, so here we already covered this. So if we run this, change this to a different name, so we're going to get a different address. Like we have showed you the layout of the memory for all those environment variables. Okay, so let's stop here.